C4H4. Again, we have another hydrocarbon, so I'm going to use carbon as my backbone. I'm only allowed to have 4 H's, so usually what happens is, here's another hint, try using symmetry. It won't work in every situation, but it can be helpful in many questions. So I have 4 carbons and 4 H's. So what I'm going to do is I'm going to put 4 H's over here. And then I've got nice symmetry. Now this carbon has 2 bonds already. So 2, 4, meaning it can have 2 more bonds in order to achieve stability, right? 2, 4, 6, 8. This carbon has 2 already, so it needs another 2 to be stable. 2, 4, 6, 8, it's happy. This carbon already has 2, 2, 4, so it needs 2 more, 6, 8. Let's take a look at this carbon. 2, 4, 6, 8. Everything seems to be good. Now I'm just going to draw the Lewis diagram to show you that everything's all fantastic with it. So for instance, this carbon has 4 valence electrons. That's fine. Each hydrogen donates 1 electron. So this one has 1 bond, 2 bonds, 3 bonds, 4 bonds, 2, 4, 6, 8. This carbon also has 4 electrons, the X's. Alright, so I haven't added or subtracted any electrons. That shouldn't be there. But it is sharing with the electrons from this carbon over here. So this one gets a 2, 4, 6, 8. So 8 electrons for this carbon as well. And same thing over here, 8 electrons and 8 electrons for this carbon as well. Now the number one question I get a lot from students is, how did you know to do this? How did you know to put an H there or the C's there or put a double bond there? The answer is because I've seen it before. Unfortunately, there is no quick or easy method to doing these line diagrams. It really is just practice, 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 seeing the different tricks and tools to use in order to stabilize a molecule. But once you've seen these tricks and you've practiced them enough, you can use them for many different situations. I like to think of it as Street Fighter, for instance. If you've ever played Street Fighter before, you know that if you push down, front, then some sort of button, either A or B, something's going to happen. So for instance, this little combo will give you a Duken for Ryu. On the other hand, if I play another fighting game that's similar to Street Fighter, like Mortal Kombat or Tekken, I'm pretty much guaranteed that if I do this down front and I push a button, at least one character in that whole game, that's going to be a special move for them. How do I know? Because I've played a lot of Street Fighter. Is there a pattern or reason to putting it down front then pushing a button? Not really. But now that I know that does something, I can apply it to different situations in the future. Similarly, now you've just seen what this does over here, or this possibility, this little tool, and you can apply this to future molecules as well. Who knew Street Fighter could be so educational? Let's move on to the next one. C4H8. So again, we have another hydrocarbon. So I'm going to use the carbon as my backbone. Again, connect them all with a single bond. So each bond represents, or each line represents 2 valence electrons. And what I'm going to do at this point is just fill it all out so that each carbon is stable. Now I'm not going to put in the H's yet because I am lazy. I know that I have too many H's right now. I mean, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means I need to get rid of 2 somewhere along the way. So usually what I like to do is I like to just play along with the lines until I've got the right structure, then I start filling in the H's. Otherwise it's just constantly erasing H's, putting them back and forth, and it's just a waste of time. So anyway, I've got 10 spaces where the H is going to go. Unfortunately, I can only have 8 H's, which means I need to remove 2 of them. So I'm just going to randomly remove the 2 from these ones over here and see what that does. So I've got now 1, 2, 3, 4, 5, 6, 7, 8 spaces for my 8 H's. That's great. This carbon is stable. It's got 2, 4, 6, 8. This carbon is also stable. 2, 4, 6, 8. But these 2 carbons are no longer stable. 2, 4, 6, 2, 4, 6. Now I do know that this carbon is supposed to have 4 valence electrons. 1 here, 1 here, 1 here, 1 here. Same thing with this carbon. 1 here, 1 here, 1 here, 1 here. So they each need 1 more electron. Well, again, there's that situation that we saw from before. Share it. By sharing their electrons, we have a double bond there now. So this carbon stable, 2, 4, 6, 8. This carbon stable, 2, 4, 6, 8. Fill in the H's. And there we have it, C4H8. Now some students usually wonder, does it matter if I put the H's at the top, above the C, or below the C? It really doesn't matter for now. Later in grade 12 chemistry, if you want to punish yourself and take that course, you will need to know, or you will learn whether the H should be at the top or at the bottom, and whether or not it makes a difference. But for now, as long as all the carbons and all the hydrogens are stable, that's all that matters. So let's try the next one, C3H5N. So this one's going to be interesting because it now has the addition of a nitrogen atom. But since it's a hydrocarbon, we're going to follow this exact same pattern we had before, use carbon as our backbone. There are my placeholders for the electrons that should be bonded to the carbon in order for carbon to be stable. Now I have space for 5 H's, so what I'm going to do is I'm going to put the H's here, 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 and here. Now let's take a look at nitrogen. Nitrogen is in group 5A, meaning that it has 5 valence electrons. As such, nitrogen needs 1, 2, 3 more electrons, meaning it can bond with 3 other elements, or at least make 3 other bonds in order to achieve stability. So 2, 4, 6, 8. So what I'm going to do is, well, take a look at where can I stick this nitrogen. Can't do it here because this carbon's already full, 2, 4, 6, 8. Can't do it here because this carbon's already full, 2, 4, 6, 8. So I have to put it around here. So I'll put it over here. Alright, so far I have bonded 1 of the bonds right here. I still have 2 more bonds to connect. Well, guess what? I've got a bond and a bond over here, nice and empty. So what we're going to do is we're going to put them here. And there we have it. Let's take a look at this carbon. Does it have 8 electrons? 2, 4, 6, 8. Fantastic. How about this nitrogen? 2, 4, 6. And let's not forget that there is a lone pair of electrons over here. So again, 2, 4, 6, 8. This nitrogen is stable. And here we have our stable molecule of C3H5N. Alright, let's move on to the next one. Now, usually when you see a formula like this, it's kind of weird, because shouldn't it be C3, because there's 3 carbons, H6, because there's 6 H's, 3 plus 3, and 1 O. Wouldn't this be easier to write? Yes, it would. However, when we write a molecule formula like this, or you see one like this, it's because they're trying to give you a hint on what the structure looks like. Here's what I mean. Let's take a look at the C. So I'm going to start reading it from left to right. So I put the carbon here, and I see that it's bonded to 3 H's. So what I'm going to do is I'm going to put 3 H's here. What's next? So I've got this one. Now I've done these 3 H's. Next, put another carbon. So I'll put another carbon over here. Next, put another oxygen. So I'll put an oxygen over there. Then next we need to put a C. And because I usually use a carbon backbone, so there's my 3 carbons. And then 3 H's attached to that C. H, H, H. Now let's take a look at the situation here. Oxygen is in group 6A on the periodic table, meaning it has 6 valence electrons. As such, it needs another 2 electrons for stability, meaning it can make another bond here and another bond here. So it needs to make 2 bonds altogether to achieve full stability. So this oxygen still needs to make a bond, and this carbon over here has 2, 4, 6, but it should make another bond as well. It has a lone electron over here. So if I have a lone electron over here, and this oxygen also has a lone electron here, because it's used up 1 here, so one of these bonds was used up, but it's still got that other electron that needs to be bonded to someone else, and so I leave it over here. So notice how these 2 electrons are empty? Well, they can connect with each other. And once you connect them, you have made a double bond. Alright. So let's take a look at it. This carbon, is it stable? 2, 4, 6, 8? Yes. Is this carbon stable? 2, 4, 6, 8? Yes. And this carbon, 2, 4, 6, 8? That's fantastic. Each of these hydrogens is fine. And this oxygen, 2, 4, and then 6, 8. Alright, so these two belong here. These two are over here. And this carbon has 4 electrons, shared one here, and over here are shared. That's what this line represents. So this electron here is there, this electron here is there. And so I symbolize these electron pairs with lines, and there we have it. So as you can see, usually when a molecular formula is like this, it's done so it can give you a hint on what the structure looks like. C, C, H3, H3, C bonded to an O, bonded to another C, which is bonded to 3 H's. And there's CH3, CO, CH3.